Alright guys, so this is the video for section 12.5. So this is the 5th out of the 6 sections of this chapter. I know it's been a struggle for some of you, but keep going. I promise you'll start getting it more and more and more. So these first couple examples are just kind of review. We'll do the first one together, then I'll have you do the second one on your own. So let's look at example 1A first. All right, so example 1A gives us like this tree-looking diagram, and it says first we're flipping a coin, then we're flipping a coin, and then we're spinning the spinner. Okay, so part A says how many outcomes are possible. So we would need to know the number of outcomes. Well, this is like a tree diagram. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes possible. Okay, list the possible outcomes. All right, so we could have a heads, heads 1, or we could have a heads, heads 2, or we could have a heads, heads 3. Or we could have a heads, tail 1, heads, tail 2, and heads, tail 3. Okay, or suppose we start with the tails. So we could have a tails, heads 1, a tails, heads 2, and a tails, heads 3. Or we could have a tails, tails 1, 2, and 3. So tails, tails 1, tails, tails 2, tails, tails 3. These would be all the possible outcomes we could have. All right, so doing this sort of thing on example 1B, it's kind of the same as what we did. I want you to go ahead and solve A, B, and C on your own, and then we will review it. All right, so let's look at this. A lot of this is just do you know your vocab. So there are 4 events, okay? So this would be event 1, this would be event 2, here's event 3, or here's event 4. Okay, and in those events, each of them have different possibilities. So event 1 would have A or B. Event 2, we could have a 1, 2, or a 3. 1, 2, 3. Event 3 would either be X or Y, and then event 4 would either be A or B. Okay, and then if we add up all these total outcomes, which is this bottom line here, there are 24 possible outcomes. All right, so let's go over some vocab. Now, there's 2 different things we're really going to be hammering this section, and it's permutations and combinations. And these are very, very similar, yet very, very different. Okay, so a permutation is an arrangement of objects in which the order matters. Okay, the order of them is important. Okay, in factorial, this is more of like a math term, and this is just the product of integers from 1 to n for any positive integer n. So if I were to write 5 factorial, I would say this as 5 factorial. All that means 1 times 2 times 3 times 4 times 5. Okay, just the product of all those numbers. Okay, and then the combination is an arrangement of objects, and now the order does not matter. Okay, and I know you're probably thinking, well, what's the difference between order matters and order does not? So let's look at something. So if I have, say I have A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. Okay, if I'm talking about a permutation, the order matters. Okay, so if I'm talking about a permutation, this is 1, 2, 3, 4, 5, 6 different things. So 6 different things. Okay, now if I have these same letters, so I have A, B, C, A, C, B, B, A, C, B, C, A, CAB, and CBA. I still have 6 things, but if I'm looking at this as a combination, I would think that these are all the same. There's one, I don't know, thing. I hate that word, but we're going to use it. One thing here, because these are all combinations of A, B, and C. Okay, so that's the difference. If I'm thinking of these as a permutation, I'm looking at these as 6 different things because these are 6 different orders. If I'm looking at this as a combination, this is one combination of the letters A, B, and C. Okay, we'll do some examples that'll make a little more sense. All right, guys, so here are a couple formulas for permutations. So if we're choosing like 4 out of 4 objects, so like when we did here, we had 3 letters and we're choosing all 3 of them, we can come up with the formula by how many total choices there are by just n factorial. Okay, but if there's more objects than what we're choosing, we would say n permutation r, which would be n factorial over n minus r factorial, okay? And here's an example here. We'll also do an example here in a minute. It'll make more sense when we do these. All right, guys, now my brain works a little different than a lot of other people's, and I know that, and I'm aware of that. And if your brain doesn't work the same as mine, that probably means you're more normal than me. But I do a lot of these using the principle of counting method, but I'll show you both ways to do it, okay? So there are 10 horses running in a race, okay? So there's a total of 10 horses. In how many different ways can the horses finish first place, second place, and third place? Okay, now this is definitely a permutation because first place is very different than second place, which is very different than third place. If you don't believe me, ask the person who owns the horse who's getting their money for their horses taken first, second, or third. First place is going to get a lot more money. All right, so here would say 10 total horses. This is a permutation, and we're choosing 3. We're choosing first place, second place, and third place. Okay, so the way I do this, the counting method, is I have first place, I have the second place, and I have third place. Okay, so then I ask myself, there's 10 total horses. So how many possibilities, how many different horses can take first place if there's 10 total? Okay, well, there can be 10 different horses that take first place. Okay, so now one of those 10 takes first place. How many is left to take second? Well, first place is already taken, so we got rid of a horse. So now there's 9 horses that can take second. Okay, well, so how many take third? Well, we already have a horse taken first and second, so we only have 8 horses left that can take third place. Okay, and when I do this, I'm going to multiply these numbers. So 10 times 9 times 8, which is 720, different ways horses can take first, second, and third. Okay, now if I do this according to the formula, I'd have 10 permutation 3, and I would use the formula n factorial over n minus r factorial. Okay, and here's my n, and here's my r. Okay, so my n is 10, so I'd have 10 factorial over 10 minus 3 factorial. Okay, so let's think of this way. Okay, so 10 factorial over 7 factorial. Okay, so just kind of a side note, 10 factorial equals 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Okay, that's what 10 factorial is. So I want you to ask yourself, could I also write this as 1 times 2 times 3 times 4 times 5 times 6 times 7? That's just 7 factorial times, I'm left with 8 times 9 times 10. Okay, it's the same way. So I'm going to rewrite this 10 factorial as that, and you'll see why here in a minute. So 7 factorial times 8 times 9 times 10 over 7 factorial. And most of you probably see it. Now, the reason I wrote it like that is because this factorial and this factorial cancel each other out. So I'm left with just 8 times 9 times 10, which is 720. Okay, so whichever way works for you, do it that way, that's fine. All right, so let's look at example 2b. It says, for a town parade, you will ride a float with your soccer team. There are 12 floats total in the parade. Okay, and their order is chosen at random. Okay, find the probability that your float is first and the float with the school chorus is second. So we want to know, we don't care about the rest of the order. We just want us to be first and the school chorus to be second. All right, so my way I do, we have first and we have second. Okay, and we're talking about probability here. Okay, so if I asked you, what's the probability of our float picking first? Okay, well, these are just random, so it'd just be 1 out of 12. Okay, well, assuming our float is first, what's the probability of the school chorus second? Remember, we're choosing random now, but we don't have 12 floats to choose from because our float is already picked first. So now we have 11, so the chorus would just be 1 over 11. Okay, and if I multiply these together, 112 times 111 gives me 1 out of 132 chances. Okay, I can do it that way. Or guys, I could do it by the formula we learned way back when. Okay, these are dependent because what happens here definitely depends on here, because notice there's 12 to pick from and 11 to pick from the second time around. So I can say the probability of A and B is the probability of A times, they're dependent, so it'd be the probability of B given A, which is just the probability of A. So the probability of us is 1 out of 12. Probability of B given A is 1 out of 11, 1 out of 132. Okay, and once again, order here matters. We want us to be first and them to be second.